Good afternoon, good morning, good evening to everyone. Welcome to the invited lecture of Dr. Špela Špenko. Špela Špenko obtained her PhD at the University of Ljubljana in 2015. She's held postdoctoral positions at the University of Edinburgh and then as a Marie Curie Fellow at the Flemish Free Universiteit Brussels. Since 2018, she has been an associate professor at the Université Libre de Bruxelles. Špela has lectured internationally at various research institutes, for example, in Kyoto, the Fields Institute in Toronto, the Max Planck Institute in Bonn. And in 2015, she received a L'Oréal UNESCO Scholarship for Women in Science. Špela Špenko's research interests lie at the intersection of non-commutative algebra, algebraic geometry, and representation theory. And now I am going to invite Špela to address us on HMS categorical symmetries and hypergeometric systems. I know that we'll have a time afterwards for you to ask questions, and the way it's set up, I think I'd ask you to put your questions in Q&A, and I will attempt to transmit them to Špela at the end of her address. So welcome, Špela, and we're looking forward to hearing from you.
Thank you very much. So I will share my screen now. And does it work? Oh yeah, yes.
Yes, yes.
Okay. Sorry. Yeah, so I was quite excited that the conference would take place in Slovenia. Unfortunately, now I'm in my home office in Brussels. However, during the presentation, I would like to evoke a bit of Slovenian spirit by showing some of its artworks. And as mentioned, I will talk about homological mirror symmetry symmetries and hypergeometric systems. But let's first start with a classical problem, namely Hilbert's 21st problem, which asks to find a linear differential equation of Fuchsian class with given singular points and monodromy group. So perhaps we should first decipher the problem a little bit. So what are systems of differential equations of Fuchsian type? Assume that we have a system of differential equations here in matrix representation, then it's of Fuchsian type if the entries of this matrix A of Z are holomorphic on C bar, so we are joined to C also infinity, except at finitely many points, A1 up to A capital N, where they have a pole of order at most 1. In particular, it turns out that linear differential equation depending only on one variable, here y, with leading coefficient 1, is Fuchsian if the familiar Fuchsian condition is satisfied. So let me add that solutions of systems of linear differential equations of Fuchsian type are appropriately bounded around singular points. So that was Fuchsian type, and now we also need to understand the monodromy. So assume that we fix a system of linear differential equations and assume that it has singular points at A1 up to A capital N. Then we choose a closed path in the complement of singular points in C bar. And assume that Y1 up to Yn form a basis of solutions of this system around gamma 0. So solutions a priori only exist locally, but we may analytically continue them along the chosen path gamma. And we denote by Y1 tilde up to Yn tilde the analytic continuations of Y1 up to Yn. So let's illustrate this on a photo of the Lake Platte. So assume that we only have Blit. We assume we only have system with one singular point, here represented by the island in the middle, and that we take the gamma, the pad that surrounds the island. And suppose that on the gray area, we have a basis of solutions y1 up to yn. And then we can analytically continue these solutions. So we extend them along this pad gamma until we come back and we get a new basis of solutions, y1 tilde up to yn tilde. Since both are bases of solutions, they should be related via an invertible matrix, which we denote here by rho gamma. It turns out that rho gamma only depends on the homotopy class of gamma. And therefore we get a morphism, turns out to be a group homomorphism from the fundamental group of the complement of singular points in C bar to GLNC, which sends the homotopy class of gamma to rho gamma. And this is what is called a monodromy representation associated to this system of differential equations. To close this discussion, we look at a concrete differential equation. So we take zy prime minus alpha y equals to 0. This differential equation has two singular points at 0 and at infinity. And we take, for gamma, this pad, we have one local solution, z to the alpha. And if we analytically continue it along gamma, we get y tilde. Then to construct the monodromy representation, we first notice that the fundamental group of C bar without 0 and infinity, which may be identified with C without 0, is isomorphic to Z. And the generator 1 here can be associated to the homotopy class of gamma. So then the monodromy representation rho sends k to the e to the 2 pi k alpha. So now that we have all the ingredients, we might restate the Hilbert's 21st problem. So what is our input? First, we have a finite set of points inside C bar. And then the second part of the input is a representation of the fundamental group of the complement of this finite set in C bar, or equivalently a group homomorphism from this fundamental group to GLNC, where n is arbitrary here. Then Hilbert asks that to find a system, given this input data, to find a system of linear differential equations of Fuchsian type, whose singular points are given by this finite set, and whose monodromy representation coincides with rho. So that's the problem. What progress has already been made on this problem? So already in 1998, Slovenian mathematician Plemal proposed a complete affirmative solution. So perhaps let me add some historical facts. So Plemal was born in Bled, that we have just seen, and he was the first rector of the University of Ljubljana that will this year turn 102 years old. He was actually one of the first Slovenian mathematicians, and I think still between one quarter or 1/3 of Slovenian mathematicians are related to him via math genealogy. Also, the subject of this talk was deliberately steered in his direction. Unfortunately, it turned out that Plemal's proof is not entirely correct. But the first counterexample was only found in 1990 by Bollybrook. And then the problem transformed into a classification of those input data that corresponds to the systems of linear differential equations of Fuchsian type. Among algebraic geometers, the focus was, however, directed to higher dimensions with a suitably rendered condition. Instead of Fuchsian type, one requires a weaker condition of regular singularities. In complex dimension 1, this means that around any singular point on the punctured angular sector, the solutions have moderate growth. This also has an algebraic interpretation which generalizes to higher dimensions. And actually, these definitions of regular singularities in higher dimensions was a cornerstone for the correspondence that we are going to see now. So that's a Riemann-Hilbert correspondence, its first version. So assume that X is a complex manifold and D in X is a divisor, a hypersurface. So before X was C bar and D was a finite collection of points. Then we have one-to-one correspondence between systems of linear differential equations on X with regular singularities in D and the representations of the fundamental group of the complement of D in X. So this theorem was proved by the linear. And let me add that there is also a version in the context of smooth algebraic varieties. And this might have been his original motivation. And very roughly, we could say that topology, here measured by the fundamental group, is somewhat determined by algebra or analysis, here represented by systems of linear differential equations with regular singularities inside the divisor. Okay. This formulation is not very precise. So now we would like to try to make it a bit more precise, and we will also refactor this correspondence for a future use. So how did we pass from left-hand side to the right-hand side? First, if we have a system of linear differential equations on X, we can restrict it to the complement of D in X. And then we looked at the solutions, but not only the global solutions, but also the local solutions. And if we take all the local solutions for all open sets U into account, we get a sheaf of solutions. So this is a sheaf of finite dimensional C-vector spaces, and it's moreover locally constant. And such sheaves we also call local systems. And once we have a sheaf of solutions, we can get representation of the fundamental group of X without D. Moreover, it turns out that all these sets can be enhanced to abelian categories, and that all these arrows are actually equivalences of categories. And now we would like to generalize this to some other systems of linear differential equations. And for this, we go on the left-hand side a bit more to the algebra directions. And we replace the systems of linear differential equations with the modules over the ring of differential operators. Then we enter the framework of D modules. So assume that X in C to the n is an open set. Then with O of X, we denote holomorphic functions globally defined on X. This stands for partial differential operators with coefficients in O of X. So in D, we have the following linear combinations where fi are in O of x, and xi here are the coordinates on c to the n. So in particular, if x is equal to c to the n, then we get the nth-while algebra. Okay. And then we might take an operator. So an element P, differential operator, an element P in D. This differential operator corresponds to a differential equation. For example, if we take the differential operator z partial z minus alpha, then we get the differential equation that we were considering before, zy prime minus alpha y equals to 0. And then the solutions of the corresponding differential equations are just all elements in O of x such that pu is equal to 0. And this can be further identified with the homomorphisms of D modules from D mod dp to O of x. So how does this isomorphism go? Assume that we have functions such that p of u is equal to 0, and we can associate to it a homomorphism that sends d to d times u. So this homomorphism is well defined because p of u is equal to 0. And then going in the other direction, so we take a homomorphism. Because this is a homomorphism of D modules, it's determined by the image of 1. So we just send it to phi of 1. This is a function in O of x. And indeed, p times f of 1, phi of 1 is equal to 0 because phi maps from D mod dp. Okay. We can do a similar thing also for a collection of differential operators. And then the solutions of the corresponding system of differential equations is isomorphic to the homomorphisms of D modules from M to O of x, where M here is represented, is defined by this exact sequence. So we have a correspondence between the solutions of systems of differential equations on one side, and then some homomorphisms of D modules. But again, it's not only global solutions that we are interested in. We would also like to know something about local solutions. And in order to do this, we should replace these homomorphisms by a sheaf of homomorphisms. So we first replace O of x by O, a sheaf of holomorphic functions on x, which to an open set U assigns O of u holomorphic functions globally defined on U. Then D we should replace by curly D, a sheaf of partial differential operators on x, which to an open set U assigns D of u, which are the following linear combinations where fi now belongs to O of u. And finally, we should replace these homomorphisms by a sheaf of homomorphisms, which for an open set U equals homomorphisms of du modules from mu to O of u. So with this, we get also a hold on local solutions. But there is another caveat to consider. Namely, we might want to compare different systems of differential equations. For example, get information from the solutions of two systems about the solutions of their union. But this solution factor is not exact. So we should also consider so-called higher solutions, the extension modules. And it turns out that with solutions, higher solutions, we will already get almost all the information that we need on the topological side. But perhaps it's a good point to ask ourselves what kind of sheaves these solution sheaves and higher solution sheaves are. So recall from the Riemann-Hilbert correspondence 1 that if M has no singularities on X, then the solution sheaf is just a local system. So a locally constant sheaf whose stalks are finite dimensional. And it turns out that this generalizes if we restrict to so-called holonomic D-modules. So they are roughly speaking those whose solutions, higher solutions, are finite dimensional. In this case, the higher solutions, so these extension modules, are constructible, which means that they are built from local systems. Or more precisely, there exists a stratification of X into a disjoint union of X alpha, such that Fi restricted to X alpha is a local system. Okay, so we have gathered quite a lot of information. We have on one side D modules. Among those, the preferred seems to be holonomic ones. And then we have on the topological side solutions, higher solutions, and the distinguished ones seem to be the constructible. We have the sheaves of C vector spaces, and the distinguished ones seem to be the constructible ones. And to compute the higher solutions, we should know something about the projective resolution of M. And a convenient machinery to process all this data and not to lose too much information is the derived category. So let A be an abelian category. For example, the category of D modules, or the category of sheaves of C vector spaces on X. So the categories that we have just seen. And with C of A, we denote the category of complexes on A. Then we say that a morphism of complexes F is a quasi-isomorphism if it induces an isomorphism on cohomology. And in the derived category, we would not like to distinguish between the complexes that are related via a quasi-isomorphism. We would like that they become isomorphic in the derived category. So therefore, we just formally invert all quasi-isomorphisms. Of course, to properly do this, it requires quite some work, but for the purpose of this talk, it will suffice to look at the derived category just as a sort of a black box where all the complexes live and which well reflects the cohomology. And moreover, if we have a functor, left exact functor between abelian categories, it induces a derived functor between the corresponding derived categories. Let's look at this on in our example. So we take for F the solution sheaf, and then the solution functor, and then the derived solution functor is such that its cohomology is given by higher solutions. So the derived solution functor contains the information about all higher solutions. It may be just a remark. So here in the notation of derived categories, we are leaving out for brevity mod. Okay. And now we are ready to state the Riemann-Hilbert correspondence in its full power and complexity, to relate all the module data with the topological data. Okay. So first we first need to restrict to the on the D module side to the complexes which have regular and holonomic cohomology, which roughly means that solutions are finite dimensional and have moderate growth. And on the topological side, we restrict to complexes which have constructible cohomology, which again means that the cohomology is built from local systems. So then the general Riemann-Hilbert correspondence tells us that the derived solution functor gives an equivalence of derived categories. So perhaps let's pause a little bit and ponder about this result. So first we notice that we don't have an equivalence of module categories, as opposed to the Riemann-Hilbert correspondence one. Because as mentioned, the solution functor is not exact. So it cannot give an equivalence of abelian categories. So we really need to pass to the derived level. And from an algebraic point of view, this theorem is quite an advancement and base generalization of the Riemann-Hilbert correspondence one, since in particular, it allows to associate to any D module a topological object, a complex of sheaves of C vector spaces. And these complexes are also rather special. They are called perverse sheaves. So not to be confused, they are usually not actual sheaves, but complexes of sheaves. And now we divert our story towards mirror symmetry. So there are some actions of fundamental groups will appear, and we will try to realize them as the monodromy representations of some systems of differential equations. But let's say perhaps first very few words on mirror symmetry. So that is a theory that has its origins in physics, or more precisely string theory. And this is a real picture of a cross-section of a space that appears in string theory. And their spaces have both complex and symplectic structure. And they come in mirror pairs, X and X naught, with a complex and symplectic structure interlaced. The complex geometry of X mirrors the symplectic geometry of X naught, and vice versa. So now we fix X as a complex manifold. So then the complex structure on X is fixed, and therefore the symplectic structure on X naught is fixed. But we still have a choice for the complex structure. And with K of X, we denote the space of complex structures on X naught. And the homological mirror symmetry conjecture says that the fundamental group of K of X should act by categorical symmetries on X, which means that it should act on the derived category of X, which here we should think of as the category of complexes, bounded complexes of vector bundles. An immediate consequence of this is that P1 of K of X acts on the complexified Grothendieck group of X, which is a finite dimensional C vector space. And it's this action for which we will be wondering which system of differential equations it corresponds to. But first we focus on the conjecture itself. By studying an example that will be the guiding example till the end of the talk. So we look at the conifold, which is defined as the vanishing locus of this polynomial in C to the 4. So it's a three-dimensional variety, which is smooth everywhere except at 0. And then we take for X an appropriate resolution of singularities of Y. In the framework of toric geometry, we may represent Y as this cone, and then to get X, we should insert also the diagonal hyperplane. But there is another viewpoint that will be more useful to us. So assume that one-dimensional torus acts on the four-dimensional C vector space. And the action is defined as follows. Then it turns out that y, the conifold, is isomorphic to the quotient of c to the 4 by this action. And to get x, one should first remove from c to the 4 some undesirable locus, so-called non-stable locus, and then take the quotient. Then physics heuristics tells us that the space of complex structures on X0 is isomorphic to P1 without 3 points, 0, 1, and infinity. And to get a hold on the derived category of X, we embed it into the derived category of C-star equivariant quasi-coherent sheaves on C to the 4, or equivalently, of C-star equivariant modules over the polynomial ring in 4 variables, where the action of C-star on this polynomial ring is induced by the action of C-star on C to the 4. And the image is generated by the structure sheaf and structure sheaf tensored with a one-dimensional representation of C-star with character 1, or equivalently by the polynomial ring and the polynomial ring tensored by V1. Then one can construct an action of P1 of K of X and dB of X such that the 3 generating loops of P1 of K of X act on these 2 generators by the following matrices. So if both perhaps think about which differential equation on K of X this representation corresponds to. And it's this viewpoint that we will pursue, an action of a group on a vector space. Because in this case, the heuristics about K of X, the space of complex structures on X0, is quite reliable. But we will restrict to actions which are sufficiently symmetric. So assume that an n-dimensional torus acts on the d-dimensional vector space. Then to get X, we proceed as in the conifold case. So we first remove from C to the D some undesirable locus, so-called non-stable locus. Here we have some choice, and then we take the quotient. And is this X for which we will address the homological mirror symmetry conjecture? So in this case, the heuristics tells us that K of X is a complement in C star to the n of a hypersurface. And this hypersurface is determined by so-called principal GKZ determinant. And in the case that the action is sufficiently symmetric, so-called quasi-symmetric, which is in particular the case if the weights come in pairs for this action, alpha minus alpha, so then K of X is a complement of a hyperplane arrangement, which can be explicitly described. So let's make a quick sanity check. And we take for X the resolution of the conifold. So X is as in the example of the conifold. In this case, K of X was P1 without 0, 1, infinity, which may be identified with C without 0 and 1. And in logarithmic coordinates, it means that we apply 1 divided by 2pi log to all the points in K of X. So what do we get? We can get all the complex numbers except for the integers. And this is indeed a complement of a hyperplane arrangement because Z forms a hyperplane arrangement in C. Because a hyperplane in C is just a point. And also note that this is an infinite hyperplane arrangement, but it's, however, locally finite. And that's also the situation in general. So in this setting, Halperin, Leissner, and Sen showed that, so in the setting of quasi-symmetric representation, they confirmed the homological mirror symmetry conjecture. So in this case, pi1 of k of x indeed acts on the derived category of x. Let me add just as a curiosity that this generalizes also to some other reductive groups. And as mentioned already before, from this we get an immediate consequence, that P1 of k of x acts also on the complexified Grothendieck group of x. And now we would like to find a system of linear differential equations whose monodromy group coincides with this representation. Again, we first look at the conifold, and we'll take the Gauss hypergeometric equation. Then one can compute the monodromy, and it's given by the following three matrices. And setting A, B, and C to 0, we see that we get the same matrices as we have already encountered before. So from this, one can deduce that this action corresponds to this differential equation, which is just Gauss hypergeometric equations with A, B, and C equal to 0. And now we change the focus a little bit. So we obtained this differential equation from an action of P1 of k of x originally on the derived category of x. And now we ask whether we can perhaps tweak a bit this action on the derived category in order to obtain Gauss hypergeometric equation also for other parameters, A, B, and C. And first we notice that the four-dimensional torus also acts on C to the 4, just coordinate-wise. And the one-dimensional torus embeds into the four-dimensional one, and the embedding is induced by the action. And this inclusion splits. And the complement is a three-dimensional torus. So it seems that we are on a good way. Before we had three parameters, A, B, and C, and now we have this three-dimensional torus. So in order to get a representation also for other parameters A, B, and C, we need to replace dB of x by a bigger category, d tilde, such that the character space of this three-dimensional torus acts on it. So the definition of d tilde is perhaps a bit too technical for this talk, but d tilde is such that P1 of k of x still acts on it. And then because this character space acts on d tilde, the complexified Grothendieck group of d tilde is a module over the group algebra of this character space, which is further isomorphic to the coordinate ring of the three-dimensional torus. And now specializing K0 d tilde at a point in this torus, we obtain a Gauss hypergeometric equation with parameters log h. Okay. And we would now like to generalize this also to other quasi-symmetric representations. For this, we first recall that hypergeometric function is a solution of the Gauss hypergeometric equation. And now a generalization of the Gauss hypergeometric equation will be dictated by the generalization of desired solution spaces. And this should be given by so-called multidimensional hypergeometric series. So they are multidimensional generalizations of hypergeometric functions. And then GKZ hypergeometric system of differential equations is defined in such a way that multi-dimensional hypergeometric series form a basis of solutions. So GKZ, due to the inventors, Gelfand, Caprano, and Zelevinsky. And now indeed, this representation gives the monodromy of a GKZ hypergeometric system. So this statement is neither precise nor entirely correct. So what should we do is, as before, replace the dB of x by a bigger category, d tilde, such that P1 of k of x still acts on d tilde, and such that the induced action of pi1 of k of x on the complexified Grothendieck group of d tilde after suitable specialization and gives the monodromy of a GKZ hypergeometric system. And these results can be extended so a bit further in analogy with D modules that we have seen at the beginning. There we also mentioned perverse shifts as the image by the derived solution functor of the category of D modules. And to state this extension, let's first recall that the representation of pi1 of k of x corresponds to a local system on k of x. And now if pi1 of k of x does not act on a vector space, but rather on a category, we may think of this representation as a local system of categories on k of x. Recall also that k of x is a complement of a hyperplane arrangement in C star to the n. And a local system on k of x extends to a perverse sheaf on C star to the n. And this also holds true for this particular action, for this particular local system of categories. So also this local system of categories extends to so-called perverse sheaf of categories on C star to the n, also called a perverse Schober, a name coined by Caprano and Schichtmann for a categorification of a perverse sheaf. Okay. Let me just add that while GKZ systems entered here the story a bit unmotivated and rather ad hoc, it's the mirror symmetry that tells us that they should be there. But the mirror symmetry is still somewhat mysterious about the exact form of this extended action. And to finish, yeah, okay, it doesn't go. It's bizarre. Sorry. To finish, let me finish on the other side of liftings. So now we are in the process of leaving symmetric harmony and trying to approach the general case. Thank you. Hvala.